Now here is the part of the lecture that might be a little provocative and controversial. If you were to ask any of my colleagues, any other professor in my department, my own department, about this class or my other class I teach, embedded systems, or even 211 and 212, most of them, probably not all, because we have a couple new people that we hired that probably don't feel this way, but most of my colleagues would say this class is probably worthless. And the reason is because they will tell you that you can solve any problem that is solvable by a computer with software. Any problem, anything a computer can do, you can make it do it with software by writing code.
Nope.
That true? Well, the question is, what do we need hardware for? Like, what do you need hardware to do? What do you have to use hardware to make a computer do that you cannot do with a Python script?
You need hardware to run software.
Right, but assuming we have off-the-shelves computers that we can buy from Best Buy and run software, why do we need? What are we going to do? Bolt extra hardware onto them? How's that work? Do we need to do that, or could we do? You could probably go to companies, a lot of companies, most companies that use computers, which is all companies now. And a vast majority of those companies never touch hardware. They only write code. They only write software. They only use software, right? So that is the fundamental sort of, I guess, problem, right? How many of you are going to be doing hardware design? Well, I think, in my opinion, which I believe is true, is that the need for hardware is whenever you have to fundamentally expand the capabilities of a computer system beyond what you can buy at Best Buy off the shelf. So specifically, there's three different things I'm talking about. The first is whenever you have to add new I/O devices, new I/O peripherals. Specifically, this has to do generally with new types of sensors and actuators, right? So if you can't measure microwave radiation with the computer that you buy from Best Buy, then you're going to need a hardware to solve that problem. You can't do it just with software, right? Because a computer from Best Buy fundamentally cannot measure radiation. Just doesn't have a sensor for that. Likewise, if you're building a robot, you need to have actuators, right, that you have to attach to it because computers aren't always robots, right? This is, now some people might say, well, hey, you slap a PCI card in, problem solved, because computers are expandable, which desktop computers generally are expandable and they're modular, except embedded systems are not. Embedded systems generally, especially the ones that get smaller, are not modular. And you generally have to design a whole new chip. This is why Apple, it's kind of amazing that this is true, but this is actually the case. Every iPhone, every iPad, every new generation of Apple products, they build an entirely new chip from scratch to power that thing. They don't reuse any chips, which is pretty nuts. New form factors. If you want to go really small, you want to put a computer inside your body, or you want to put a computer in your clothes, or you want to have, I don't know, watches, new form factors. And when I say new form factor, I'm talking about size, how much power or energy they require. If you want to go ultra low power, right, you got to build some exotic hardware to deal with that. Or if you want to make them radiation hard or something, you want to put them in space, you want to add fault tolerance. Generally speaking, that requires some sort of hardware change. But in this class, we're mostly going to talk about the third item here, which is performance. And when I say performance, I'm talking about runtime, how long does it take to run a program, as well as things like, can you do certain things in real time? Like, for example, can you record 4K video, which is fundamentally a real-time problem, which we haven't always been able to do until just recently. Or how about 8K video, which no computer in the world, well, maybe I guess a RED camera might be able to do that. Super, super expensive device, right? So I'm talking about performance factors. You want to change the performance. You want something that can do something performance-wise that nothing else can do, then you got to do hardware. Now, some people are also surprised to learn that computer processors haven't gotten any faster in 10 years, virtually. What I'm talking about is the performance of software. If you take a program, the same program, and run it on a computer 10 years ago and have it run on a computer today, it'll be faster, but it's not going to be nearly as much faster as you would expect from 10 years of computer development, computer processor development. And why is that? Well, I have assembled here, this is my table that I built just from poking around. These are what I consider to be the peak performance indicators, meaning that these all represent the upper bounds for how much performance you can get out of these chips. So for example, clock speed. Clock speed is a fundamental concept inside a chip. It's how fast individual data path operations and register transfer level operations can happen in a chip. You can see that clock speed has changed very little in 10 years. Actually 12 years now. This table's getting a little long in the tooth. Peak integer instructions per cycle, this is the number of instructions one core can execute in one cycle, has only doubled in 10 years. And even that's the peak performance. And it turns out that the actual achieved IPC is much lower than that and has grown even smaller. In other words, in theory, you can do 8 instructions in a cycle on an Intel processor, but it almost never happens because of resource constraints in the architecture. Max number of cores, I guess most of you probably have noticed this. I mean, we start out with 4 core and we're really just, these are desktop processors, by the way. Server processors, you can get them in bigger varieties. But on the desktop, you really can't get anything bigger than a 6 core. And that was 4 cores 12 years ago. Memory bandwidth, which is another major factor in performance, because a lot of code is limited by how fast you can talk to the memory. It's called the memory wall. That hasn't changed at all until just recently when DDR4 memory came out, and even then it didn't even double. Peak floating point has increased the most dramatically. It's gone up by a factor of 8. But you can't use this capability unless you write vectorized code. So you have to write very specific type of programming to take advantage of this, and it has to be floating point, and most programs don't use floating point. And then level 3 cache, this is kind of how much level 3 cache you have on, and this has changed very little. I mean, it's gone up by a factor of 4 in 10 years, but it's kind of leveled out here at the end. This is another plot. This is just to kind of prove my point, because that last table was something I came up with. This is from a guy that was giving a talk at Cornell who I believe he got this data from Intel. So this is basically Intel's data. This graph looks a little busy, but I'll explain it to you. This is plotting 1, 2, 3, 4, 5 different characteristics of processors. And these aren't just Intel processors, a bunch of processors going back all the way to 1975 up to 2015. And you can see that on the red line here, these red dots represent the number of transistors on the chips. And you can see that this is, this line is linear, but it's on a logarithmic scale, meaning that this line is increasing exponentially. And this is Moore's law, in which the number of transistors, which are the basic elements of the basic hardware resource of computation, the basic devices you put on a computer chip, they double every 18 months to 2 years, and they're continuing to do so. And it used to be that as the number of transistors doubled, the performance you'd get, which is this thing labeled spec int performance, this is basically just runtime of a benchmark program, the integer benchmarks. You can see that these two curves are perfectly parallel to one another, meaning that the runtime, the performance in runtime was not only directly proportional, but literally it was very, very consistent with the number of transistors up until, oh, look at that, 2006. That's exactly the same year that my table started, basically 10 years ago. At which point it changed its slope, and now it's only increasing at 15% per year. Now you can say, well, 15% per year, that's still exponential. That's still pretty good. But there's obviously this divergence here. Likewise, if you look at frequency, it's even flatter at 9% per year. And the number of cores is, well, there's not a whole lot of data for that because we didn't even have multi-cores until 2004 or so. But that slope looks to be about the same as frequency, about 9% per year. Now, if you look at this one, power, you can see that up until about just over 2000, the amount of power CPUs took was also increasing exponentially. You could see that there would have been a line here. They didn't put the trend line here, but there would have been a trend line here that would have been linear here on this logarithmic slope. But once it hit about 300 watts, that was it. You can't really feasibly use more power than that. So it had to flatten out, and this became what's called the power wall, meaning that we can't have processors consume any more power, but yet we're demanding more performance out of them, and we have more transistors, right? So that's the problem. And so this graph would have you believe that it's the power wall that's actually causing these slopes to level out, not anything else. This is just a power problem. I don't know if I entirely agree with that. This is another chart that I made. This one has a lot of stuff on it, but you can see I've got Intel processors, these again desktop processors from 1982 all the way till right now. Actually in the future, because Cannon Lake didn't even come out yet. Number of transistors, you can see that according to my data, Moore's law didn't really kick in full swing until 1997. That's when things really literally started just doubling with every generation. But you can see that as of 2000, the frequency pretty much stopped at 4 gigahertz, and that was the end of that. So the frequency stopped scaling at 2000. And then if you look at the number of cores we have on the chips, that stopped with Ivy Bridge at 8 cores or so. That was the end of that. And then something interesting just happened recently. Intel has this thing called tick-tock, where they have this tick, which is they come out with they scale down the process technology, right? So the transistor size, which is this column, gets smaller. And talk is when they improve the microarchitecture. And they go through this pattern, right? And it's interesting because they just stopped doing that just recently. They had the Broadwell and the Skylake came out. And then that was at 14 nanometers. And then everyone expected there to be the 10 nanometer chip, but it never happened. Not only did it not happen, but they came out with KB Lake, Coffee Lake, and Whiskey Lake, also at 14 nanometers. So it almost looks like Intel's having some trouble even reducing the transistor size. So something's going on there. If you look at GPU technology, this one's kind of crazy. Nvidia has had 6 generations of their GPU, and they're just flying here. They're still doing Moore's law, and they're increasing number of cores still. But you can see that if you take the number of transistors per core, this number is actually going up. So it looks like that the number of cores seems to be leveling out. Like the Pascal and the Volta are both capped at 64 cores. But the number of transistors has gone up dramatically. So Nvidia has taken an approach where they're pretty much, it looks like they may be stopping being able to add more cores, and they're putting more transistors to speed up the individual cores. So how long can this Moore's law thing go on for? So Cannon Lake is the one that was supposed to have already been out but hasn't come out yet. It's supposed to be at 10 nanometers, which gives us about 5.2 billion transistors. I know after the 10 nanometer, it's supposed to be 7 nanometer, but at this rate, it should have been like 2022, but I don't know if they're going to get that deadline. How far can they keep going? Well, if you look at silicon atoms in a semiconductor, chips are made out of silicon, and the silicon atoms form this crystalline structure using covalent bonds between 4 neighboring atoms in the crystal at different angles. The spacing between the atoms is a half of a nanometer. So you obviously can't, you're not going to be able to go any smaller than that. You probably can't even get really anywhere near that, because you got to have at least you got to have at least multiple atoms to make up the transistor channel, right? So, but we know we certainly can't go smaller than 0.5. That's the size of the molecular spacing in the crystal structure. So yeah, clearly, something's got to give there eventually. Now the question is, people ask, well, wait a second. So you say that processors haven't gotten any faster in 10 years, but transistors still increasing fast. Seems to be sort of unabated. So why is it that we can do new stuff? Like recently became able to record 4K video on a phone, and recently getting better graphics, continually getting better video game graphics. Oculus Rift just, recently, well, I guess it's been out for a while, but it's pretty amazing. What's up with that? Well, the answer to that question is revealed if you take a look at the chip, the processors. This is a micrograph, which is just a photograph through a microscope, of a second generation core processor. This would be a 32 nanometer Sandy Bridge processor. And it's kind of cool because Intel, they always release these things and they mark off using these yellow boxes what each region on the chip is doing. And you can see that this is a 4-core processor, shown there by 4 cores. There's a shared level 3 cache, which is pretty obvious because the cache structure is nice and regular. The cores are all over the place, very irregular, right? But look at this. They have this system agent memory controller, which includes all this I/O stuff, and this processor graphics here, which is kind of curious. They use quite a bit of the real estate. Then we go to the 4th generation Intel. This is the 22 nanometer chip, 1.4 billion transistors. And it seems like the processor graphics part is a little bigger in this one, as is potentially this part. Kind of hard to tell, but definitely the processor's graphics there are bigger. Then we get to the 5th generation, and well, now the cores are, less than a third of the whole chip. Now, this is a little misleading because this is a picture of a dual core. So if this were a 4-core, it would look a little different. But even so, you can see that the processor, the graphics here, they're investing much more into the graphics there. And then you get to the Skylake, the 7th generation Skylake. Also 4 cores, and now you can see that once again, not quite as small as we might expect, but the CPUs are pretty small. And the other thing that's kind of interesting is look at even the last level cache, which is level 3 cache, seems like it's kind of deprioritized, de-emphasized there. Now, if you look at embedded chips, let's look at Apple. I mentioned Apple comes out with a new chip every generation. These are pictures of the A5 all the way up to the A10 Bionic. I think it's a Bionic, right? I think that's the latest one, A10. I've highlighted, these are a little harder to make out because they're not quite as, Apple isn't actually these came from a third-party website, Chipworks I think it's called. But they're not labeled as clearly, but you can see that, you probably can't make it out, but I put the white box to show where the actual CPUs are. Everything else is not CPU. So GPUs, DRAM, interfaces, and all these other coprocessors in here. So you could see that in all these, the CPUs are pretty small. What's in the Qualcomm Snapdragon 835? That's the one that's in the Galaxy S8, probably the 8, not the 9, 8. One of the latest Samsung Galaxy phones. That chip, it's one chip. It contains two wireless transceivers, the LTE, which is the cell modem, and the Wi-Fi module. And it has no less than 7 different types of processors. It's got a hexagon DSP for voice recognition. It's got a audio processor, which is called the Acoustic. the Quistic audio processor, the ISAT location processor. They actually have an accelerator for the damn GPS. Adreno GPU, Qualcomm Spectra 180 camera processor, so this processes the pictures and the video. And it has a security coprocessor. And then it has this Cryo CPU, which is actually just an 8-core ARM processor. They call it the Cryo CPU, but it's ARM architecture. So this kind of answers the question, right? You see where I'm going with this? The idea is that on embedded systems and even on desktop CPUs, there is this clear shift of basically giving up on CPUs. Because we're not going to get new capabilities out of making the CPUs run software faster. It's impossible. The only way to get new capabilities out of computers is to build hardware, build specialized coprocessors to do very specific things like 4K video encoding, 3D rendering, security, voice recognition. All that stuff is actually doing just those things. There's application-specific processors or domain-specific processors, depending on the different terms. And anything else would be running on this CPU and is not really going to, just having the software is running software on this CPU versus one from several generations ago isn't going to be much faster at all. Make sense? So the whole idea is that Moore's law is now, it used to be that Moore's law made CPUs faster. Now Moore's law is just allowing people to add more specialized processors onto the chip. Okay, so that's the end of my sort of spiel about why hardware design is important. Because in the future, there's going to be an increasing amount of hardware design. Now, especially considering when Moore's law runs out, now you're going to have a fixed budget of transistors and a fixed budget of power. So then it's going to be there's going to be some aggressive designs that you're going to have to do in there to get new capabilities. Now, modern CPUs, let's talk a little bit about design. This class is ostensibly about design. The modern CPUs, as I mentioned, they have about 250 million gates, logic gates. You guys remember logic gates from 211, right? Like and or and that kind of stuff. Now you might say, wait a second, I thought you said they have 1 billion transistors. Yeah, but it takes like at least 4 transistors. Well, to make a 2-input logic gate, you need at least 4 transistors. You can do an inverter with 2, and an AND gate, a NAND gate, 2-input NAND gate, you need 4 transistors, right? So you have to divide the number of transistors by 4 generally to get the number of gates. Now, that's a little inaccurate too because a lot of those transistors are things like caches and on-chip memory, which don't translate directly into gates. But just for the sake of argument, let's take the 1 billion transistors, divide it by 4. That gives you on the order of or close to around 250 million gates. If you use breadboards to design that thing like you did in 211, it would require 8 million breadboards, which would be over 1,000 miles long end to end, which would be obviously impractical. So the question you might have, or that at least I hope you have, is how are modern chips designed? Like, especially when you think about how many gates there are there, that must be astronomically complex to design. How do you design something with 1 billion transistors? How does that even work? You probably, you haven't seen anything up until this point in the curriculum concerning that yet. So, in addition, you have to also consider, once I design something, how do I reuse it? How do I give it to someone else to use? How do you give someone a piece of a chip to put in their chip? Right? How does that work? And then test and debug. How do you know that the chip's working? How do you test it? That kind of stuff. So in this class, we're going to cover hardware description language, HDL, also known as RTL, register transfer language. Never understood why there's 2 names for the same thing. It's the same thing, RTL, HDL. It's a programming language for hardware. It's kind of neat. It's a programming language you write in a text editor that gets turned into hardware. How does that work? It's used for modeling. So it's a language that has concurrent semantics, meaning that every line of code represents essentially a circuit, and every line runs at the same time concurrently, meaning that you can mix up the order of lines in your code and it won't make any difference. It'll behave the same way. Not true in any other sequential semantic programming language like Python or Java, right? You break your program if you randomly resorted the lines of code. It's also used for modeling. In fact, it was originally designed for modeling. Modeling meaning that the Department of Defense wanted to buy custom chips for tanks. They needed a chip that did something very specific. And they were like, okay, we can write it down like in English prose what it's supposed to do. But that is problematic because you can interpret English prose in different ways, and it's not necessarily going to comprehensively capture the behavior of this chip that they're trying to order from this supplier. So what do? Well, you just develop a programming language that describes in a precise way what the chip is supposed to do, and then you use that as kind of a formalized specification that you can then send, right? And then people came up with ways you can simulate it in software, like simulators, and then eventually synthesizers, where you could take an HDL description and go through a process called synthesis, where you can transform it into hardware. Now that hardware can be gate level hardware, like gates that are connected, or transistors that are connected, or you can represent, you can specify that hardware in different ways, but HDL was a way to design hardware. HDL works basically by leveraging two concepts that are basically the same thing. I don't know, again, this is a little redundant, but the first is abstraction. Abstraction is the idea, and you've probably heard of abstraction from your programming classes. The idea of abstraction is that you just want to hide details that aren't important, right? So, for example, you've got devices. What's a device? Device is a transistor. So every time you talk about transistor and Moore's law and feature size, that's devices. Devices is the smallest element of a digital circuit is a device, transistor. And so you can use those devices to build gates, which we'll learn at the end of this. I'm going to cover that at the end of this lecture. But those actually create analog circuits, because you're actually building transistors form analog circuits. Now, they're supposed to look like digital circuits, but if you look, they're in analog. You try to make them always be 0 or 1, but they're actually analog circuits. Once you have a library of those circuits, then you can realize those you can conceptualize those as a standard cell library, or a library of cells or gates, primitive logic primitives. And then, now keep in mind, by the way, when you build gates, you're only building your standard cell library. Typically, there's like 12 gates. All you have to do when you do this is build a very small amount of these gates from transistors. We used to do this in my VLSI design class, 613. We build a standard cell library from scratch with transistors. You might say, oh God, that must be horrible. How many gates could there be? No, there's just a few. You keep it real simple, very small set of gates that you can use. But once you've got those, you can use those to build very complex logic structures. You can start assembling these gates together, even though you only have a small repertoire of gates. So you can design them really well because there's just a small number. But you can use them to build essentially any kind of digital logic circuit. So at that point, the sky is the limit, but you still want to kind of keep it simple. You want to build simple parts. You want to build a simple ALU, a simple register file, a simple multiplexer, that kind of stuff, decoder, like that. And once you've got that set of things, which again is relatively small, you can assemble those into a microarchitecture, which is where you start building data paths of a CPU. So you have a register file that connects into an ALU, which connects back into the register file again, and you can implement things like instructions. And then once you've got those, you build that into an architecture, which defines all the different sort of the native language, the native set of instructions that a computer can can execute. Again, fairly limited set. Oh, Intel's got tons of instructions, but considering the total number of programs out there, it's small. And then from there, you can build on operating systems and application software. So everything is built on top of one another. When you get a job, you're always at one level of this. You generally don't go up and down. So you can get a job working to develop these standard cell libraries, in which case you spend all your time just trying to build gates out of transistors. Or you can be the guy that's building logical components. Or you can be the guy that says, I'm going to take those logical components and I'm going to build things like a USB host adapter that we can sell to Apple and have them put in their A11 chip, that kind of stuff. So everyone's sort of at one level of this abstraction. There's also this concept of hierarchy that comes up a lot, and it's basically the same thing, except it happens inside of a design. And if you look at this sort of from the top down, you've got your CPU. What's a CPU? What's a bunch of processors? What's a processor? That's a bunch of functional units and a register file. What's a functional unit? Well, it's got a floating point adder and a floating point divider in it. What's a floating point adder? Well, it's basically just a comparator, a shifter, and an integer adder. Well, what's a comparator? Well, a comparator is a subtractor. Well, what's a subtractor? Well, it's an adder. Well, what's an adder? That's a bunch of full adders. Well, what's a full adder? It's an XOR gate. And that's it. Now you're done. That's how you can resolve this really complicated thing, and you sort of divide and conquer it into these levels of abstraction. Now you can work from your top down, or you can go from the bottom up. Generally speaking, you go from the bottom up. You try to build up all of these things and assemble them into more complex structures. So that's pretty much how, when we're going to learn a language called System Verilog in this class. And System Verilog it uses this a lot. In fact, most System Verilog code is called structural code, which is essentially just components that are interconnected, almost like a block diagram, like a schematic, just written out in code. Make sense? Relatively small amount of Verilog code is behavioral code, where you're actually, trying to write code that is eventually will be decomposed into gates. Make sense? So there's a lot of this kind of, you have to get used to this idea of hierarchy and abstraction. It comes up over and over again in hardware design.